Hello. You have learned that most hot solids give off white light. White in the sense that they have a continuous spectrum. On the other hand, hot gases emit light that has a discrete line spectrum. Now, if you pass a beam of white light through a gas, you will obtain what is called an absorption spectrum. It basically looks like the continuous spectrum, but with some discrete dark lines in it. This dark line corresponds to some wavelengths that have gone missing from the continuous spectrum. So what happened to those wavelengths? First, let's discuss how photons can excite atoms. Let's say our gas atoms have these three allowed energy levels. And let's say the gas atom is hit by a photon with energy of 1.4 electron volt. Now you are currently in the ground state with energy of negative 2.0 eV. Absorbing this photon will bring it to the energy level of negative 0.6 eV. But negative 0.6 is not an allowed energy level. As a result, this photon will pass right through the gas. It cannot be absorbed by the atom. I know you're going to ask, hey, why can't the atom absorb 1.0 electron volt? Yeah, if it absorbs only 1 eV, it can excite itself from n equals to 1 to n equals to 3, and it let the photon keep the balance of 0.4 eV. Now, for some reason, photons are different from electrons. If it's an electron with 1.4 eV of Ke, the atom can always absorb just 1.0 eV and let the scattered electron keep 0.4 eV as its Ke. But if it's a photon, that's not possible. The atom must either absorb all of it or let it pass. I like to imagine that it's because the photon doesn't want to change its color. Because if it goes from 1.4 to 0.4 eV, it changes energy, it changes wavelength, it changes color. Maybe the photon is not happy with that. But that's just a joke lah, huh? So for some reason, the photon energy must be exactly equals to the energy gap. If not, the atom is not able to absorb that photon. So for example, if the photon has an energy of 1 electron volt, which matches this energy gap, right? Then yes, it may be absorbed, the photon will be excited to n equals to 3, and when it de-excites, you emit photons of these energies. What about 0.8 electron volt? This one will pass right through, because absorbing 0.8 will mean that we go to negative 1.2, and negative 1.2 is not an allowed energy level. So the atom is going to say pass. What about 0.6 electron volt? This matches this transition exactly, right? So the gas atom can gobble up this photon, be excited into n equals to 2, and when de-excites, you re-emit this photon here. What about 0.4 electron volt? This one is obvious. This one will pass right through. Okay, now imagine if we try to pass these 7 photons through the gas. So on the other side of the gas, you may find that you have only 5 photons left. What happened to the 0.6 eV and the 1.0 EV photons? They got absorbed, right? Because they matches these two up transitions exactly. And when the gas atom de-excites, you emit photons of these energies. Okay, now imagine we're trying to pass a beam of white light through the gas. So this is the white light, right? With a continuous spectrum. And these are the gas atoms of that gas that the white light is going to pass through. So if you examine the light that have passed through the gas, you're going to get the absorption spectrum. It's a continuous spectrum, but the discrete dark lines correspond to photon energies of 2.0, 2.5, and 2.7 electron volts. The gas allows photons of all energies to pass through, except those with these 3 energies. What happened to the photons of these 3 energies? They got absorbed by the gas. So when a gas de-excites, they'll produce photons of these energies, including the 2.0 eV, 2.5 eV, and 2.7 eV ones. So the absorption spectrum is kind of like the continuous spectrum minus the emission spectrum. So just like the emission spectrum, the absorption spectrum is proof that gas atoms have a quantized energy structure. It's because it has discrete energy levels. That's why it's so choosy, so picky in what kind of photons it can absorb. Now, students like to ask this question. Since the gas atoms re-emit those photons that you have absorbed, won't they fill in these dark lines? Meaning we get back the complete continuous spectrum. Now that's a very good question. So let me explain. So you got the white light, you look in this direction, you see the continuous spectrum. Now you insert the gas in between, you get the absorption spectrum because the gas has selectively absorbed certain wavelengths. But this gas is now excited. So when it de-excites, you re-emit those photons that it has absorbed. But when it re-emits, the gas re-emits all the photons in all directions, uniformly in all directions. So the photons which were traveling this way, that got absorbed, when they are re-emitted, only a tiny fraction were re-emitted in the original direction. The majority of them are re-emitted in all the other directions. So because of this, the dark line here do not get filled in. If you look at the gas from this direction, if you look from this direction, you see the discrete line spectrum. And the emission lines here match the absorption lines here. Another thing I want to highlight is the dark lines in the absorption spectrum is actually not completely dark. Not all the photons that can be absorbed by the gas actually ended up being absorbed. It also depends on how thick this gas is. If the gas is not very thick, then a lot of photons can actually just pass right through the gas without coming across any gas atoms at all. But as long as a fraction of those photons got absorbed and the intensity got reduced, it's usually sufficient for them to show up as dark lines. It's a matter of contrast, right? Okay, that's all. Ta-ta!